you can start.
My name is Belozerova Maria, and I want to present to you my talk, Asymptotic Behavior of Solutions to Stochastic Differential Equations with Interaction. And now I'll turn my camera to make my internet better. And the aim of my talk is to show the example of asymptotic behavior of distribution of mass of interacted particles in the stochastic flow. The interest to such objects is caused in particular by the phenomena of intermittency that is described, for example, in the works of Zeldovich and Molchanov. Shortly, intermittency is the contrast between the realization and mean characteristic of speed or density in turbulent flow. One of the first articles devoted to this phenomena is the article of Zeldovich-Molchanov. The next simple example of intermittency is the next one. Here, psi j are independent, identically distributed near one random variables. And we consider logarithm psi, that is the sum of logarithm of psi j. And then every logarithm of psi j is identically distributed near 0. For large n, we have that psi is equivalent to exponent of square n eta, where eta is normal distributed with 0 mean and dispersion sigma. But in contrast, the expectation of psi is equivalent to exponent of n sigma square divided by 2. Main object of our consideration is the mass distribution of particles in stochastic flow. This object was considered by many authors. Let us mention some results. We consider the equation 1. Here, fst from x is the position at time t of a particle that was in an earlier time s in the position x. U is the Gaussian random vector field with known expectation and covariation. The probability measure mu t is carried by a stochastic flow. The next result belongs to Kunita. Suppose that for all x from Rd, the covariation matrix A is strictly positive defined. Moreover, suppose that one-point motion under F has an invariant distribution pi, and pi of Rd equals to 1. Then for every Borel set in Rd, the average limit of the integral of mu t equals to invariant measure. And if one-point motion doesn't have a finite invariant measure, then expectation of mu t of Borel set R tends to 0 as t tends to infinity. In the paper of Greg Zirbel and Erhan Silner for isotropic Brownian flows were established the asymptotic behavior of the expectation and the covariance matrix of mass distribution in the flow. On the basis of well-known results about the limit behavior of one-dimensional diffusions, Baxendale and Harris proposed the description of the limit behavior between different particles in the isotropic Brownian flow that depends on the main Lyapunov exponent of the flow. And they proved that if the dimension of our space is more or equal than 4, or if d is equal to 3, but the main Lyapunov exponent is greater or equal to 0, then the distance between our solutions tends to the infinity almost surely. If d equals 3, but the main Lyapunov exponent is less than 0, then the t converges to either 0 or plus infinity. And all other cases are considered except of the case if d equals to 2 and the main Lyapunov exponent is greater or equal to 0. But the particles can move in the flow and in the same time react to each other. In this case, coefficients of corresponding stochastic differential equations will depend for some characteristic of positions of another particle. The next stochastic differential equation with interaction was considered in works of Andrei Anatolyevich Dorogovtsov. Such equations describe the previous situation. Here, mu0 is the probability measure that plays the role of perverse distribution of the mass of particles. X from ut is the trajectory of the particle. And this particle left the point u at 0 time. Ut characterizes the distribution of mass of particles at the time t. The above results of Zirbel-Zillner and Baxendale-Harris indicate that in many cases the distribution of mass of particles has the next property. The particles are not far from each other, but the center of the mass behaves like some diffusion process in finite-dimensional space. This fact annotated the appearance in the work of Dorogovtsov, Andrei Anatolyevich, and Karlikova MP. The concept of shift-compactness. We call the set of measures mu alpha to be shift-compact if for all alpha there exists some vector u alpha in Rd, such the set of measures mu alpha minus u alpha is compact. And we consider the next example that shows that behavior. We consider the equation 7, and it can be checked that for every u, the solution tends to infinity as t tends to infinity. But we can understand also that the distance between solutions not increase on t. Then the measures mu t minus x from 0t, the shifted measures, has a weak limit as t tends to infinity. The next theorem of Andrei Anatolyevich Dorogovtsov and M.P. Karlikova gives the conditions under which the set of measures mu t is a shift compact. So in multidimensional case, we have the shift compactness, but in one-dimensional case, using the order between particles, we can prove more refinement results. And Maria Karlikova continued the study of a one-dimensional case of differential equations with interaction, and she got a result that there exists a limit that characterizes distance between solutions. Based on this, Maria Lagunova-Karlikova proved the following interesting analog of iterated logarithm law. For this, she considered more concrete type of differential equations, 13, and she proved the next theorem. Here B is global Lipschitz with some constant L, supremum B is less than infinity, and mu0 has finite moment greater than 1. And then we have the next result. Let us notice that here the limit can be random. And the next example shows such situation. Due to presence of interaction, the upper limit in the law of iterated logarithm occurs to be random here. So we consider such a limit. The considered results shows that research of the distance between solutions are important for studying of the behavior of mass in random flow. And now I want to present my own result for a two-dimensional case. Here, the right part satisfies the next condition. Let us notice that condition 18 is similar to conditions in the theorem of Andriy Drogovtsov and Lagunova about the shift-compactness. So it is in some sense natural. And by these conditions, we can have the representations about the distance from x from ut and x from 0t. It is 19. And for this representation, we have the next result, that such limit exists almost everywhere. Here the function phi big depends also from the distance between x from ut and x from 0t. And there is a sketch of proof. At first, I count the characteristic of the martingale, and it became the next value, the sum of the next integrals. Then, by the random time change representation, we have that the sum of these martingales is such a linear process of characteristics. Then look on our function phi big, and by the conditions of our equation, we have the next two-sided expectations on phi big. And then we have that the difference between x from ut and x from 0t and this integral of phi is greater than 0 if t is bigger than 0. Then we look again on our representation for distance between xut and x0t, and we understand that our integral of some pk in square is less than tau u, where tau u is the time of the first strike of minus norm u by the process wu. And then we have that with probability 1, the next limit exists almost everywhere. And we have the representations of the representation of this limit. By the condition of the right part of equation 14, they are stronger than in the theorem of Andrei-Drogovtsov and M.P. Karlikova. They have one-sided estimations, and there are the two-sided estimations, and one side is the same. So by this theorem, we have that the set of measures mu t is shift compact. By the proving the result and by the considering the equation, we understood that two-dimensional situation is in some sense similar to one-dimensional. And we are sure that the limit that we get is positive, but now we can't prove it formally. And then maybe there exists some limit mapping like in one-dimensional case. And thank you for your attention.
Okay, it is a very short talk, but nevertheless, maybe somebody have questions or comments? I have such question, Maria. You mentioned that under your conditions you will have shift compactness. Yes. So can you substitute this? Can you show us the slide with this function phi, big function phi, which you subtract? Oh, this one.
I'll
this
show.
one. No. Oh, this one.
Here's the function phi.
With your statement. Oh, here is. Okay, so can you substitute this integral with big function phi just by one function which does not depend on u small? So is it possible just to have one such function, or it is not possible? What do you think?
No, phi depends of u, and on phi to understand how it behaves, I can show again my estimations on this phi, and I understand that it depends essentially of u because there are distances between x from us and x from u0s.
But you mentioned you still mentioned that the family of measures will be shift compact. But of course, it does not mean that the distances from the those vectors which we subtract from our measures will be fixed. But we can have such hope, and it will be very interesting in this case to find precisely the shifted family from our theorem with Karlikova, and compare this family with your function, with your integral from function phi grade. Do you understand what I think?
Yes.
Okay.
Thank you very much.
Okay, so please do it. It will be interesting. Some other questions, please. Okay, if there are no any questions, we have today some rest. But next talk will be provided by Professor Xia Chen from Knoxville about the Anderson model and long-time behavior of solutions in this model. Okay, thanks everybody, and goodbye.